Welcome to today's paper reading. Today's paper is titled, InseRF, Text-Driven Generative Object Insertion in Neural 3D Scenes. This paper was published on the AR14 preprint by Mohamad Shahbazi and colleagues from ETH Zurich and Google Zurich. InseRF is a novel method for inserting new objects into 3D scenes reconstructed by NeRF. It operates based on a user-provided textual description and a 2D bounding box in a reference viewpoint. The field of 3D scene editing has seen significant advancements due to the integration of text-to-image diffusion models, which provide strong priors for 3D generative modeling. However, existing methods primarily focus on editing the style and appearance of 3D scenes or removing existing objects, leaving the challenge of generating new objects unresolved. InseRF addresses this gap by proposing a method that grounds the 3D object insertion to a 2D object insertion in a reference view of the scene. The 2D edit is then lifted to 3D using a single-view object reconstruction method. The reconstructed object is inserted into the scene, guided by the priors of monocular depth estimation methods. This approach allows for controllable and 3D consistent object insertion without requiring explicit 3D information as input. Figure 1 illustrates the generative insertion of objects in 3D scenes. Instruct NeRF to NeRF can alter the overall style of scenes or perform edits with a strong positional prior, such as placing a mustache on a face. However, it struggles with inserting objects in arbitrary locations due to multi-view inconsistencies. In contrast, our method ensures multi-view consistency by design and can insert new objects in user-specified locations. Recent advancements in novel view synthesis and generative modeling have significantly improved methods for generating and manipulating 3D assets. Diffusion models and their integration with neural reconstruction methods like NeRFs have enabled powerful 3D generative models for various applications. However, current 3D scene editing methods are mainly limited to simple, object-centric scenes, leading to 3D inconsistencies and lack of spatial control. To address these challenges, the authors propose a method for scene-aware object insertion in 3D scenes, using a 2D reference view and textual description, without requiring explicit 3D spatial information. In the field of 3D scene editing, recent advancements have integrated 2D text condition diffusion models into 3D generative modeling. Methods like Instruct NeRF to NeRF use an iterative approach to edit different viewpoints of a scene, though they face challenges with 3D consistency and localized edits. InseRF addresses view consistency through viewpoint correspondence regularization. For object removal, some studies rely on multi-view masks, while others use single-view annotations to generate multi-view masks. Object insertion remains less explored. Methods like Vocal Dreamer and language-driven object fusion show promise but require specific user inputs and have limitations in scene complexity. The method described in this paper takes as input a NeRF reconstruction of a 3D scene, a textual description of the target object to be inserted, and a 2D bounding box in a reference rendered view of the scene. The output is a NeRF reconstruction of the same scene containing the generated target 3D object placed in a location guided by the 2D bounding box. The method consists of 5 main steps: creating a 2D view of the target object, reconstructing a 3D object NeRF from the generated 2D view, estimating the 3D placement of the object using monocular depth estimation, fusing the object and scene NeRFs, and optionally refining the fused 3D representation to improve the insertion. The refinement step involves rendering images from different viewpoints, refining them using a 2D diffusion model, and optimizing the NeRF. This process enhances the capability of the refinement step by focusing on more frontal views and using multi-view object masks. Figure 2 illustrates the process of inserting a new object into a 3D scene using our proposed method. The process begins with a single reference view of the scene, annotated with a 2D bounding box and a text prompt describing the object to be inserted. A 2D edit is then generated, showing the object in the specified location. This 2D edit is subsequently transformed into a 3D model of the object. The 3D placement of the object within the scene is determined using depth estimation techniques. Once the object is correctly positioned, the 3D representations of the object and the scene are fused together. An optional refinement step can be applied to enhance the appearance of the inserted object. This method ensures that the new object is inserted in a 3D consistent manner, without requiring explicit 3D spatial information. In this section, the authors detail their training and evaluation procedures. They use NeRF 360 adapted to hash grids for the NeRF representation and evaluate on real indoor and outdoor scenes. The method is compared to two baselines, InstructNeRF 2NeRF and Multiview in painting. The authors highlight that their method only requires a rough 2D bounding box, unlike the baselines which may need more detailed inputs. Visual results show the method's ability to insert 3D consistent objects, with comparisons to baselines provided in Figure 4. More visual results and detailed baseline implementations are available in the supplementary materials. Figure 3 showcases examples of using InseRF to insert an object into the neural representation of different indoor and outdoor scenes. The method demonstrates its ability to insert 3D consistent objects into various scenes, highlighting its effectiveness in placing objects on different surfaces, a challenging task in the absence of exact 3D placement information. Figure 4 presents a qualitative comparison of object insertion methods. IN2N alters existing objects rather than inserting new ones, and the in-painting baseline struggles to generate geometry at the desired location. In contrast, our method successfully inserts new 3D consistent objects at the specified locations. Figure 7 illustrates the impact of the refinement step on object insertion within the scene. As shown, the refinement process significantly enhances the texture details and lighting effects of the inserted objects. This results in a more realistic and higher quality appearance of the objects within the scene. The refinement step is crucial for achieving a seamless integration of new objects into existing 3D environments, ensuring that the added elements look natural and well integrated. Figure 5 illustrates the impact of scale optimization on object insertion within a scene. The figure demonstrates that without optimization, the object's placement can be inaccurate and unrealistic. However, with the proposed scale/distance optimization, the object's placement becomes more realistic and closely aligns with the original 2D edit. This optimization step is crucial for achieving a faithful and accurate representation of the object within the scene. Figure 6 illustrates the critical impact of scaling the densities when merging the object and scene representations in NeRF. Without accounting for the rescaling of the object NeRF during volumetric rendering, the object fails to be accurately displayed in the synthesized views. This figure emphasizes the necessity of the proposed density scaling adaptation for correct rendering of the fused NeRFs. In this study, the authors introduced InseRF, a method designed for generative object insertion in 3D scenes. The method requires a textual description of the desired object and a 2D bounding box in a single reference viewpoint of the scene. InseRF generates objects in a 3D consistent manner by leveraging the priors of 2D diffusion models and single-view object reconstruction methods. The proposed method successfully integrates these components for in-scene object generation. Evaluations and visualizations on various 3D scenes demonstrated InseRF's capability to generate 3D consistent objects without the need for explicit 3D placement information. Thank you for watching.